It's another my great pleasure to introduce the second speaker of this session. Is Professor Ki-ahm Lee from Seoul National University, and he got PhD in, I guess, 1998 at Ki-ahm under the supervisor of Louis Gabrielli, and he got some award. First one, maybe Excellent Research Paper Award from Korean Maker Society in 2008, and another one is Scientist of the Month from National Research Foundation of Korea in 2012. And now he got award invited section lectures today. Also, he's going to talk about homogenization theory in nonlinear PD. And please welcome Professor Ki-ahm Lee.
Okay, well, it is my great honor to have a chance to make a talk at ICM. I really thank you for organizers and the IMU. And even though I'm a Korean, this is my first time to be in this complex. So as a mathematician, I'm not sure whether I'm going to have another chance here. So if I major economics later, so who knows. All right, so there was a serious progress in the homogenization theory in the last 10 years. And I'm happy to join such activity. So now I'm going to talk about the homogenization theory in nonlinear partial differential equations. The outline is the following. First, I will introduce what is the homogenization theory, and I will discuss homogenization in perforate domains, and non-variational problems, low-dimensional oscillations, and convergence rate. So, the homogenization theory is concerned with the derivation of homogenized or effective equations satisfied by the limited solution of the differential equation with the rapidly oscillating data. So let's look at the first picture. So blue dots are distributed periodically inside of white materials. So if you look this picture a little bit far away, then you're gonna see this picture with a smaller periodicity. And if you look at the picture really far away, then the material looks very homogeneous. So we are asking the property of this material having oscillation in smaller scale. And if you zoom out unicell in this picture, X represents physical variable, which is called macroscopic or slow variable. And Y is called microscopic or fast variable. So such a physical property can be formulated mathematically with the PDE, and I just started with this. I just give a simple example, which is a Differential boundary value problem. And here the diffusion coefficient is oscillating periodically in this variable. Forcing turn is periodic in this variable, and also boundary data is periodic. Also, you can think nonlinear version of that equation. And then, what is the main questions? So we usually ask the existence of the limit of U sub epsilon. In order to do that, we really need a uniform estimate to extract a convergent subsequence. So here, you do have a PDE with very rough data. So we ask what is the uniform estimate? That is another thing here. And the other one is a homogenized or effective equation satisfied by U. And this equation really tells you the property of the material after homogenization. And then to find the homogenized equation, usually what I do is the following. The correctability condition of U to be U epsilon becomes homogenized equation. So there are large of possible functions, but the limit U is very special. Why? Because it's a limit of U sub epsilon. Such a specialty is kind of addressed by a correctability condition because they are so close to each other. And the last one is the convergence rate of U sub epsilon to U. and then we will consider higher order correctors to match the convergence of the higher order. Okay, let me start with the very simple one-dimensional problems. So my x and y variables are just one-dimensional, and then my diffusion coefficient is oscillating like this periodically. And I put the boundary data 0 and 1 here and solve this Lee. Then you can derive the solution easily since it's ODE. Then you end up with this solution. And this solution can be decomposed into two parts. So, which is the first one is U of x, and that is x here, and that is the global behavior of the solution. And epsilon w is the oscillation around there. So U is the limit of use of epsilon, and epsilon of W is called corrector. Why? Because if you add this corrector to the solution, then that one will be the solution of the epsilon problem. So actually you can correct the limit configuration by adding corrector. And then the limit equation will satisfy this equation, and the diffusion coefficient, the effective diffusion coefficient is simple harmonic averaging in this problem. So let me review a little bit well-known method. The first one is multi-scale expansion. So now I think the divergence type equation with oscillating diffusion coefficient. So you simply expand your solution with respect to this order epsilon and plug it into the equation. Then you're going to have lots of equations. And you group them in, with respect to the order. They match the orders in this side and that side. Then you're going to have a list of the solutions inductively. Then the first solution really tells you this first order term, zero order term, is independent of this oscillation through the Lubin theorem. Then our limit solution has no oscillation. Okay. And so that you see. And then that's the first part. And second equation really tells you the correctors, which I discussed before in picture. And the third one tells you really the homogenized equation. Well, this is a divergence type equation. This is a right-hand side. And if you take an integral of this divergent structure in a unit ball, then the integral is zero by integration by part. So integral of this one is zero. And such a condition give you this homogenized equation. So this is a very heuristic argument. If you want to justify, there is a problem. So if you write down that equation in terms of the variational form, then you have this one. And diffusion coefficient is oscillating, and it has weak convergence, and gradient of U to the epsilon has a weak convergence. Multiple of weak convergence may not converge. So the idea of Tata is replacing this test function with an oscillating test function. So here, this is a standard test function. You correct it with the corrector. And the thing is the following, like the equation tells you the divergence of this one is good, and the curl of this one is zero. So even though they converge weakly, but they do have a very special structure. So by the dB column, this integral converges. Okay. And now, well, recently there is a lot of activity in the viscosity method. Well, let me go over a little bit what's the meaning of viscosity solution. So that if you look at the textbook, there are a lot of definitions in different problems. But roughly saying, the viscosity solution is a continuous weak solution having a comparison principle when it is compared with another classical solutions. So if you have some very nonlinear problem, if you want to define the viscosity solution, so that could be the maybe minimum requirement. And what is the uniformly elliptic fully nonlinear equation? Well, this is a kind of nonlinear order 1 equation perturbed from the Laplace equation. So this is the definition. And the value is growing with this amount for the positive matrix. And if this large number and small number is 1, you end up with the Laplacian. So in the other words, if you change a different value, then operator has a perturbation from the Laplacian. And the first part is the convergence. So if you look at the work of the Ki-ahm, then there is a Holder regularity. So you can get a Holder regularity, then you can extract convergence of sequence. So as we see the picture before, our solution is a very small oscillations around the nice picture. And this estimate is true if you have a small oscillations, but I will point out a large oscillation later. And existence of corrector can be found in this way. But let's say you try to solve this equation for given any symmetry matrix M, but generally it's almost impossible to solve it. So what happens is that there is a uniform, there is a constant lambda, so that there is a periodic function W satisfying this equation. And this lambda is depending on the matrix M, so we can write down in this form. And if our operator is Laplacian, then this one is just a trace. And then we can easily show that one is a Laplace operator, kind of. All right, so then theorem, and this is the result by Evans. And homogenized equations satisfied by U will have this one now. So the heuristic reasoning is the following. It's very important in further talk. So if you expect this is the limit, then that is very special, as I told you, because it's a limit of epsilon problems. Then somehow it should be very close to the solution. So it should be correctable to be a solution of an epsilon problem. How? By adding this corrector to this polynomial. Then we expect it to satisfy epsilon problems. And you plug this one into original equation, then we end up with this problem, which we discussed before. And this equation has a solution when there is some specific number lambda, which it has this form. And if we expect this one is a solution, then this one should be 0. In the other words, f bar d square of p. D square of p is m, here the polynomial. So p will satisfy this equation. So in the other words, the correctability condition of polynomial is almost equivalent to saying the homogenized equation of the quadratic polynomial. Okay, so recently there have been active progress in viscosity method, and Ki-ahm Lee, Spanidis, Ishii, Matano, Evans, Theorem, and also their student, Malad, Inongi, Sun Che, Henry Chagolian Water 2, Armstrong, Schwab, and so on. And also now our student. So Farma, Songwon, Songhang, Okkan, and Martin, and Binha, and many of them will be here now. And also there are interesting books regarding homogenization. The first picture that I showed is from this textbook that I read at early beginning. And also the other books are very good book, and I got inspired by their result. Okay. Let's think about the perfect domain. So perfect domain is just like this picture. So you have a domain omega with a periodic holes. And if you magnify the if you look at the unit cell, then epsilon represents the periodicity, and the A sub epsilon is the size of the hole. And this is our material that we are talking about now. Oops. This one is sensitive. And now we are going to consider oscillating obstacles. So obstacle, so pi is the obstacle. It has this shape. Now, in order to create oscillating obstacles, what you do is, whenever you see the hole, then you keep the obstacle outside the hole, you delete the obstacle. So then you will have a lot of needles in this shape. And that one is distributed periodically with a different height, depends on the part. Then we look at the least super solution above this obstacle in this form. Then we end up with 3 scenarios. So A sub epsilon is the radius of the hole in our problem. A sub epsilon to the star is a kind of critical rate. So first case is the following. Let's say our obstacle is too thin. So in the other words, A sub epsilon is much smaller than critical rate. Then it is so thin, so the limit solution will get no influence from the existence of obstacle. So in the other words, the limit function will just simply satisfy standard Laplace equation. And let's say the second case is a supercritical one. So the obstacle is too deep. So then the solution will be influenced fully by the existence of obstacle, and then become a solution of obstacle with the obstacle pi of x. So problem doesn't change at all. But if obstacle has some critical rate, then as you can see in this picture, so the limit function will be like this. Okay. So in the full supercritical case, the obstacle will push up the solution. But here it's critical, so you push up partially. So therefore the limit solution will have a partial influence from the obstacle. So then this partial influence will change the equation. And let me point out the issues in this problem. So in this problem, L-infinity oscillation of the solution stays very large, even though epsilon goes to 0, so-called large oscillation. In the previous problems, oscillation of U of epsilon goes away, which is a small oscillation. For the Laplace equation, the Dirichlet energy of U sub epsilon is controlled by energy. So you have energy estimate, so you have reconvergence things. But for the fully nonlinear equation, there is no corresponding energy. So actually there are lots of homogeneous solutions, but they do have different energy levels. So then we use a more geometry method and then we will construct a super sub-solution to capture oscillation of U sub epsilon by bending homogeneous solutions. And then this is the result with the Ki-ahm Lee, and then this is the critical rate, and this is the term by the partial influence of the obstacle. And this result is well known for the Laplace operator, but mostly is a gamma convergence method. But since we are thinking about the fully nonlinear operator, we will prove it through geometry method. For the fully nonlinear operator, so our operator is uniformly elliptic and positively homogeneous of degree 1. So if you put the positive value, it comes out. And we needed this condition to get a homogeneous solution, and we consider the same obstacle problems. And then for the Laplace operator, there is a fundamental solution. So then we can use that fundamental solution to create a super sub-solution. But for the fully nonlinear operator, we needed a replacement for that. And this is the result with Lewis. And for this type of operator, we have 3 types of the homogeneous solutions. And first one is just like a fundamental solution in the Laplacian for Lee. And second one is like a logarithmic solution, like a 2D problem for Laplacian. And this one is like a 1D problem for the Laplacian. Anyway, we have homogeneous solutions, and we got it through the Hanach estimate. And then we can create the critical rate, and also we end up with the homogenized equation. Here, the influence from the obstacle will come in nonlinear way, so we do end up with nonlinear operator. Okay, so then in order to carry out those arguments, so let me show you how to think. The first one is question is how to find the critical rate. So as I told you, the constructing correct is very, very important. That will give us crucial information. So let's consider this problem. So now we are looking at the periodic bounded solution. And if k is 0, well, constant is a solution, no secret at all. Now we solve this equation above the obstacle. And this is a subcritical, and this is supercritical, and this is critical case. Now what's going to happen is the following. If our obstacle is too thin, then even though you put a very, very small number here, still oscillation is getting larger and larger, epsilon goes to 0, because it's so thin. So the shape is just like a fundamental solution. If the obstacle is too deep, then even though you put a very, very large k, still the oscillation is very small, eventually goes to 0. So we choose the thickness of the obstacles so that this periodic solution has order 1 oscillation. That's the first thing. That's the way to get the critical rate. And then, now, well, let me go back a little bit here. The influence of the solution, obstacle comes in this way, and this is the capacity. So after getting a critical rate, we need to find out the influence of capacity. So then the way is the following. So at a critical rate, if you put some number, then you have oscillation of obstacles, periodic solution. And we choose k so that the size of the oscillation is just 1 unit size. Then for the Laplace operator, so this is the case. For the Laplace operator, if this oscillation is 1, then this k is a standard capacity. For the fully nonlinear operator, I don't know whether there is a capacity theory. Like if it is a Hessian type equation, then you have integration by part structure, so you can define the capacities. For the fully nonlinear operator, you don't have a integration by part, so I'm very excited to have a kind of capacity concept right here. And the other ingredient is a kind of uniform estimator. Since the L-infinite norm stays constant, so we need a uniform estimator to extract converging subsequence. So if you look at the picture, so my epsilon solution has zeros near the obstacles. But if you look at the pictures, and if you choose a periodic point, then the values at this red dot, well, maybe the values near obstacle is very high and here it is low. On the other hand, if you look at the values at the red dot, a periodic point, then they are pretty similar to each other. And that will give us a discrete gradient estimate. And then, if we chop off some neighborhood of the obstacle, so we are removing the zeros, then we have a small oscillation here there, and it can be proved by Hanoi estimate. And if you combine them, we have global epsilon Lipschitz estimate. Then we can extract a converging subsequence. And the other problem that we considered in the appropriate domain is soft inclusions. Soft inclusion looks like this. You have a diffusion equation, and you have no flux condition under the boundary. So, and this is a appropriate domain we saw before. And then we consider what if our operator is very general? But that is a very standard thinking. And then we end with one big problem. So that is the comparability condition. So for the Laplace Neumann value problem, so let's say you want to find a periodic bounded solution with this Neumann boundary value problem, then there is a comparability condition. So you take an integral over right hand side and the Laplacian integration by part and so on, you end up with this condition. And if you have these conditions, then you have bounded periodic solution. So that is the standard comparability condition, as you know. Then for the general operator, what is the comparability condition? Here, the most important thing is integration by part structure. But we don't have integration by part. So somehow, why, and I ask myself, why do we think a comparability condition anyway? In order to get bounded periodic solution. So let's think it reversely. Then, idea is the following. Existence of a controllable global periodic solution implies comparability condition for equation. So what does it mean? So in the system, diffusion and flux condition are competing to each other. If you have a bounded global solution, that means that they are somehow balanced. Yeah. So, and then we showed there is a unique gamma satisfying these Neumann value problems. For any direction xi, then we find this gamma, and this gamma, we call this gamma as a comparability constant. And we say the equation satisfies comparability condition if this constant is zero for any xi. And definitely will standard Neumann condition for Laplace operator satisfy this condition, and we created a couple of non-trivial examples. And then if we try to make homogenization, we do a symptotic expansion as we did before. Then there is epsilon order term, epsilon square order terms, and so on. And this first term, and we call it first corrector, is used for correctability condition. And so this, what existence of this one really tells you the flux condition and diffusion conditions are balanced. Then we used this second corrector to find homogenized equation, and we end up with a certain conclusion. And let me give you related works here. And also we consider the parabolic version, also degenerative equation or force medium equation have been studied. Well, this is a highly oscillating obstacle problems. So as we saw, constructing a homogeneous solution is important. In this parabolic problem, it translated to nonlinear eigenvalue problem. So we did the homogenization in the nonlinear eigenvalue problem first to capture the degeneracy of the equation. And then we used that on as our homogeneous solution and created the super and sub-solutions. And also with the Martin and the Mina, we consider the homogenization of the thin obstacles where a low-dimensional obstacle may go through perforate domain partially. So this is a really interesting issue which I'm going to talk about later. And then the number theory plays a very important role there. And the third subject is non-variational problems. So homogenization of a variational problem with energy involves the standard average of oscillating data frequency. For example, oscillating diffusion coefficient will be averaged out as a harmonic mean, as we discovered in an early example. And oscillation of lower terms will be simple average at the limit. At the homogenization of non-variational problems, which I'll give you a couple of examples, the effective equation could be different from simple averaging. Then we can find the frequency at the variational problems. So it requires different techniques. So let me a little bit go over the flame propagation. So the model equation looks like this. U represent amount of reaction materials, and this is the reaction terms. It's burning. So amount of reaction material goes down. And this is a reaction term, and this is the reaction rate, combustion rate, which is a periodic. So in the other words, you have a certain material which is distributed periodically, and it's burning. So at different position, you have a different material, so you have different reactions. But they are distributed periodically, so reaction rate changes periodically. And then this delta represents the thickness of the flame. And if delta goes to zero, the flame front is a really low dimensional problem. So, and it's moving, so we call it free boundary. Then we end up with this type of equations. So in the parallel type, you have use of T here, and this is a stationary flame. And there is a diffusion equation inside. Under the flame, you have a reaction kind of terms here. And we consider the 1D problems. Well, I will show you the picture later. And the interesting part of this problem is there are multiple solutions. And there could be energy minimizer, minimizing the corresponding energy, or smallest solution, largest solution, and so on. So, let's think the slopes of the, because this is the gradient condition under the free boundary, and if you average out, then you're going to have a constant here. So, after homogenization, you're going to have gradient condition under the free boundary. So, if you look at the energy minimizer and smallest solution, you have a following limit configuration. So this is the limit of energy minimizers. Then the slope will have this one. Then as you see, this is the average of F. And if you look at the smallest solution, how can you create the smallest solution? If the gradient is the largest, then you get a smallest solution. That's why you get a maximum here. So the slope of the limit of variational problem, energy minimizers, will have this one, including this average, simple average. And the slopes of the limit of U of non-variational problem will have a maximum of that. So this example tells us the homogenization of the smallest solution of non-variational problem is genuinely different from that of solutions of variational problem. And then, what about the two dimensions? So if you look at the energy minimizer, the limit of energy minimizer, then free boundary condition is a simple average. So your gradient is the same at every location directions. Then your solution ends up with this solution with a circular free boundary. Now, if you want to have a smallest solution, you want to decrease the size. So one of the ways is the following. So this plane is also a solution. And then you take a minimum of between this planar solution and this energy minimizer, then there will be a super solution. So therefore, my smallest solution is smaller than this super solution. And what happens is the following. This smallest solution is a very strange free boundaries. It has a flat spot right here and around it. So the important thing is the smallest solution has a flat spot in their free boundary. Then what is the free boundary condition in this problem? And then the result is the following. So this is the simple case. Then the free boundary, even though it has a flat spot, we can show the free boundary is C1. And the gradient is between the average and the maximum value. And actually, maximum gradient will achieve maximum value at the center of flat spot. And then it will decrease to the average as the point will approach to the end point. And then similar statements are true for general periodic function, f. So this is a kind of new free boundary problems. So we are working on the regulator of this with this new free boundary problem with my student. Well, it's a very interesting issue. New species somehow in this area. And if you look at the parabolic version, then there is a pulsating wave, which is a turbulent wave, like oscillating wave, trapped by two standard turbulent waves with the same constant reaction rate and with the same speed. So this only difference is I put the time derivative right here. If this is zero, then that is the problem that we considered. And then this is the standard turbulent wave if this is 1 or constant. So U represent amount of reaction materials. So if U is 0, then there is no material. In that also, it's a bond zone. And if U is positive, then it's a phase zone. So here, the junction between them is a flame front, which is moving. And in the result with the Caffarel and the Malat, we consider the homogenization of pulsating wave when the thickness of the flame is much smaller than periodicity of reaction materials. And the interesting part is that if you try to track down the front, you should scale space and time in the same scale. If you scale it, you end up with an elliptic problem. So classifying the elliptic solution, which has the almost constant slope, and we create plane-like solution, is very important. And then choose the smallest one among them, that will be the effective reaction rate. Then, so the effective reaction rate for turbulent wave is proved to the minimum of the slope of plane-like stationary flame for the directions in which turbulent wave moves. In addition, the oscillation of free boundary of use of epsilon will converge to zero uniformly through the another estimate. And then the other issue is the low dimensional oscillation that I'm going to discuss. And question is, what if oscillation happens only on the low dimensional hypersurface? So for example, oscillating boundary data, Differential or Nonlinear data, it happens only low dimension. Or oscillating free boundary problems, highly oscillating thin obstacles of flame propagation, or evolving hypersurface with oscillating speed. And the open problem for the oscillating boundary data was proposed by Suganidis when I visited Vancouver. It was 2009 or 2010. And then when I heard of that problem, so it looks a very similar problem that I considered before, like a stationary flame problem that I discussed. So I got some idea and I made a joint work with Minau and Henning Chabolian, Inong Kim, and Sunny Che. And to understand the issue, let's consider the very simple case. We have a Laplacian and the boundary data. One boundary is fixed and the other boundary data is oscillating. And there are three possible limits of limiting energy, limit of energy minimizers. Then there are serious difficulties in those directions. So the first difficulty is the following, the dependence on the direction. For example, let's say this is my boundary. And if it lies in this way, so its normal direction is E1. My boundary data is periodic in this way. And if this is my boundary, then my boundary C only, with my boundary C, my boundary data only partially. But if my direction is transversal, then oscillation happens here and here. So basically this boundary see all of the boundary value. So what happens is the following. If the boundary is n-1 dimensional hypersurface, which means the average of G of G sub epsilon along the hyperplane may be different from the simple average for like this one, because it doesn't see all of the value. How can it be simple average? And the other phenomena, my boundary is fixed, but the oscillation periodicity is changing. So this is the fixed boundary, and then this is the configuration when I have a epsilon 1 periodicity, and this is the other configuration with a epsilon 2 periodicity. And if you look at this one, and translate it into a model 1 picture, the fixed boundary is actually oscillating in the model 1 picture. So there is oscillation of the boundary in the model 1. That's another phenomenon. So even though the boundary is fixed, the boundary in model 1 oscillates, and then U sub epsilon takes all of the possible values at different epsilon. So in other words, this is a very small tiny zone, my values change quickly. So even though my boundary is fixed, it will take different values at different epsilon. So if the boundary data is chosen at a maximum, then we look at the limit soup. If it is chosen at the minimum value, then limiting input will be chosen. And also energy minimizers. And if you consider the Neumann problem, there could be no solutions in Neumann value problems due to the compatibility condition. That could be another issue. And let's consider the homogenized equation. So if you look at the limit soup and the limit inf, then it will have a certain effective boundary data right here. So, well, since it's a limit soup, I denote it like this, and it is a limit inf, so I denote it like this. So question is, what are the values, right? And if my direction, normal direction is E1, then I can choose the supremum of G. Still, I can take a U sub epsilon, so that the boundary value of U sub epsilon is a supremum. So, and also you can take an infimum. So this is the largest one among possible boundary data, and this is the smallest one among possible boundary data. If my direction is E1, then there will be the supremum and infimum. But my direction is, if my direction is transversal, then they are equal to simple average. So what about the higher dimension? So there is a rational direction and irrational directions. So if my normal vector to the hyperplane is a rational directions, then, well, as you see here, so I start from here, then I'll come back here in model 1 picture. So in other words, this line, if you change this plane in model 1 picture, then this plane will cover unit cube only partially. So in other words, my boundary C only, the boundary data only partially. But if my direction is irrational direction, by the Weier's equidistribution theorem, the hyperplane with the irrational normal direction covers a unit square in model 1. So you may expect a simple average. So in other words, rational direction plays like E1 direction before, and the irrational direction plays like some transversal direction in previous example. So it has a lot of work, but pretty much like that. Then if you look at the Laplace equations, then you have a green representation theorem. So you look at the boundary data through the integral. So we take hyperplane with a given direction at given point, then look at the average there, and take the limit soup among possible boundary value. and take an infimum among the possible boundary value, and we denote like that, and there is average. And the result plays like at the interior, you end up with a simple average, but the boundary value will lie down between these two values, two possible values. And you can justify through the green representation, and if the direction is irrational, then these two values will be same. Then your boundary value will be simple average. For the fully nonlinear operator, there is no green representation formula. So question is, what's the average with respect to the fully nonlinear equation? How can you find the G upper star lower star without the integral? And then that can be carried out through the correctors. So let me give you a brief idea here. If you give me the plane, that is the boundary, and inside you have equation, under the boundary you have oscillating boundary data. Then if you are away from the boundary, then it averages out. So that, and then you choose the largest one, smallest one among them. They will play like a G upper star and lower star. And therefore, at the irrational direction, your boundary data will be, effective boundary data will be continuous. And the irrational direction is not continuous, but still you can capture the size of oscillation. The oscillation of boundary data depends on the oscillation of K nu mod 1. So we get a similar phenomenon at the highly oscillating linear obstacles, and there is a capacity issues and convergence rate, and I'm learning time. So, and it really depends on the discrepancy of the number. Okay, last slide. Sorry. That is not last time. This is a convergence rate. I will allow just one slide. And then now we consider convergence rate, and this is the, you have oscillating diffusion coefficient, and this is the effective equation. And then our solution will converge U with this epsilon order. And there was a heavy research on those issues by Ki-ahm Lee, Nonlinear, recently Kennedy too. And then we look at the higher approximation there with my student Sang-Gi. Then we have a full expansion like this. And then this is the correctors from interior, and this is the correctors from the boundary layer. Then we got this estimate. And also we got a similar result for the fully nonlinear operator. But the thing is, really you need a regulatory theory to carry out your ideas. So that's the great theme of those problems. And thank you for your attendance.
Okay, anyone have some questions? We don't have enough time. Otherwise, okay, go ahead.
If you put your obstacles on a hexagonal lattice, something changes. Like you have like Dirichlet coordinates, right? Cubes and squares where you put your obstacles.
Yeah. Well, that really doesn't change that much. Yeah,
Put them on the, like when you have and the density, when you control the density.
Okay, why don't you
maybe
continue during the break? And the next talk will start exactly 5 sharp, right on schedule. Okay, thanks, speaker again.
Thank you.